Have you ever stopped and wondered how the internet actually works? I mean, really works? Deep down, it's all run by this incredible set of rules, kind of like a universal language that lets all our different computers and phones and gadgets talk to each other. That rulebook, it's called the OSI model. And, for about 40 years, it's been the solid foundation of all networking. But today, we're going to do something cool. We're not just going to explore what it is. We're going to look at how the totally bizarre world of quantum physics is forcing us to write a completely new chapter. All right, let's get into it.
Just think about it for a second. You type up a message, you hit that send button, and boom, almost instantly, it pops up on a screen halfway around the world. It really does feel like magic, doesn't it? But it's not. It's actually a super organized, step-by-step journey, and following that journey is the perfect way to understand the model that makes it all happen. Okay, so before 1984, computer networking was pretty much the Wild West. Seriously, every different company had its own system, and none of them could talk to each other. It was chaos. So the International Organization for Standardization, or ISO, stepped in to clean things up. They created what's called the Open Systems Interconnection model. And the genius of it was that it took this incredibly complex process of network communication and broke it down into 7 distinct, manageable layers. So let's follow a little piece of your data on its big adventure. The main idea you gotta get your head around is something called encapsulation. Okay, imagine you're sending a physical letter. First, you write the letter itself. Then you stick it in an envelope and write an address on it. That's one layer. Then the post office might toss that envelope into a mailbag for a specific city. That's another layer. See? Each step adds its own wrapper with specific instructions. As your message travels down these 7 digital layers, it just keeps getting wrapped in new envelopes, getting it ready for its trip across the network. Starting right at the top, with you, the application layers get your data ready. Then, the transport layer comes in and chops it up into smaller, more manageable pieces called segments. Think of it like breaking a long book into individual chapters. Next, the network layer slaps addressing information on those segments, like putting the destination country on a package, turning them into packets. Then the data link layer gets them ready for the local part of the journey, kind of like adding the specific street address. Now they're called frames. And finally, the physical layer turns the whole thing into a raw stream of ones and zeros, a bit stream, ready to be shot through cables or beamed through the air.
Let's make this super real. Mr. Cooper hits send on his email. That message immediately starts its trip down the layers. The application, presentation, and session layers handle things like picking the right protocol, maybe compressing the data so it's smaller or encrypting it, and opening a stable line of communication. Then, just like we saw, it gets segmented, packaged up into packets, then frames, and finally becomes that stream of bits heading out into the wild. And when it gets to Miss Palmer's computer, the whole process just happens in reverse. It unwraps the message layer by layer until it pops up perfectly readable in her inbox. Cool, right? So the most important takeaway here is that each layer has a very specific job to do. Layer 7 is the one our apps talk to. Layer 6 is the universal translator. Layer 5 is the conversation manager, opening and closing the line. Layer 4 makes sure your data actually gets there reliably. Layer 3 is like the global postal service, using IP addresses to route data between different networks all over the world. Layer 2 is more like the local courier, using MAC addresses for devices on the same network. And Layer 1, well, that's the raw hardware, the cables, the Wi-Fi signals, the stuff that physically sends the bits. For decades, this model has been the absolute bedrock of our connected world. But what happens when the fundamental laws of physics that you've built your entire model on just change? This is the huge challenge that quantum networking throws at us. See, the predictable, orderly world of classical bits, which can only ever be a 0 or a 1, is being totally disrupted by the bizarre, probabilistic reality of quantum bits or qubits. A qubit can be a 0, a 1, or somehow both at the same time. This opens up incredible possibilities, for sure, but it also completely breaks all the old rules.
The entire internet that we use every day is built on a few core beliefs. We assume data is predictable, and, this is the big one, we assume we can copy data perfectly. I mean, think about it. If a chunk of data gets lost on its way to you, what does your computer do? It just asks for another copy. It's so simple. This ability to just duplicate data for backups and error correction is absolutely fundamental to how everything works.
And this brings us to the giant conflict. In the quantum world, there's a law called the no-cloning theorem. And it basically says you cannot create a perfect, independent copy of an unknown quantum state. It's just forbidden by the laws of physics.
Well, that completely shatters our main strategy for fixing errors. We can't just ask for another copy. And on top of that, quantum states are unbelievably delicate. The tiniest disturbance from the outside world can make them lose their information. That's a process called decoherence. It's like trying to send a secret message written on the surface of a soap bubble. The old rulebook is totally useless here.
So, how in the world do you build a network when you can't copy information to fix mistakes? You can't just slap a bandage on the old model, you have to fundamentally redesign the whole thing. And so, researchers are now proposing a really bold evolution of the OSI model, one built from the ground up to handle the strange but powerful logic of quantum mechanics.
So, what's the big idea? Well, instead of trying to cram these new quantum behaviors into the 7 old layers, the proposal is to expand the stack itself. We're going from a 7-layer model to a brand new, groundbreaking 9-layer model.
And as you can see, the original 7 layers we know and love are still right there in the middle. But now, they're sandwiched between 2 powerful new layers. At the very bottom, we have a new layer 0, the quantum substrate, and way up at the top, a new layer 8, the cognitive intent plane. Layer 0 is basically where the model meets the actual physics. Its job is to manage the core quantum weirdness that the classical model just had no idea what to do with. This includes stuff like generating entangled particles. These are pairs of qubits that are mysteriously linked no matter how far apart they are. It also handles processes like quantum teleportation, which is a way to transfer a quantum state from one place to another without physically moving the particle itself. This is the new foundation that makes everything else possible. So if layer 0 is the quantum foundation, layer 8 is the intelligent brain of the whole operation. You see, managing a quantum network is just ridiculously complex. It requires constant real-time adjustments across all the other layers. So this cognitive intent plane uses AI and large language models to act as a kind of orchestra conductor, figuring out what the network needs and intelligently adapting everything from routing to security on the fly. So there you have it. We've gone from the simple rules that first connected our computers to a new, pretty mind-bending framework designed to connect quantum states themselves. And this opens the door to things like truly unhackable communication, incredibly powerful distributed quantum computers, and probably technologies we can't even begin to imagine yet. It really leaves us with a fascinating question to chew on. The first internet gave us a global web of information. What will an internet built on these strange and powerful rules of the quantum world truly unlock?